Swayam Prabha. Digital India. Educated India.
We've been talking about multi-objective optimization for a while, and this course is about that, so that's quite appropriate. But we give you an introduction to optimization in general, its scope, and starting with point based, then we moved to population based and went into some details, right? Now, yesterday we talked about evolutionary way of doing multi-objective optimization, and you've seen the advantages and of course disadvantages, right? You need a population, so you need some memory to work with it, but these days that's not an issue. But the advantage you get with finding number of solutions simultaneously is tremendous, rather than one by one. And we have lots of examples of parallel search ability that these methods have. When you do one by one, you actually lose all the information from the previous run. But if when you're doing EMO, which is evolutionary way of doing multi-objective optimization, you actually can gain from one individual's superiority in the population. If one is close to the Pareto set, this can bring in the other individual. So that's really the advantage that we have. So if you think of how that happens, it's actually with the crossover operator. So many people try to leave out the crossover because they say most of the time it doesn't produce anything good. That's because you haven't thought properly. You are using maybe just a standard crossover operator that has not much meaning to the problem you are solving. So again, I want to reiterate that here is that coming up with a customized operator set like crossover, mutation, selection, there is not much to customize, but you can still do how you take care of multiple criteria. In NSGA2 we do it some way, SPA2 pays they do in some other way, and there are new algorithms which I'll introduce you tomorrow when you talk about advanced methods like NSGA3, MOEAD, they do it differently. So you could do some there, but I think problem specific operators are mostly crossover and mutation, and you can always introduce something more on top of that. Okay, so today I'm going to talk about EMO and decision making, maybe separately, together, all possible ways, right? Because unless you do the decision making, okay, which I'm talking about here, you are not talking about the whole story, because in multi-objective optimization you get a Pareto set. Most papers in our field, if you read, that will be their last figure before conclusion, right? They don't do the decision making part. If you are handling test problems, like you suggested a new algorithm, now you want to test how good it is compared to the existing literature, of course there is no point of decision making, because to a numerical problem with objective functions have no meaning, how can you do decision making, right? What to decide there, because these objectives are artificial objectives. But I'm talking about even lots of practical problems where people are solving and trying to publish. They don't do that extra bit of decision making, but that's, I think, equally important. Like I showed you step 1 and step 2. Step 1 is optimization, find a Pareto set. Step 2 is decision making, pick a solution. For the problem context, now you're talking about a problem with maybe cost, environment, cost, safety, all of these things. And if you don't do the decision making, what does a user do with all those solutions? You have to also tell that story. So that's what we're going to talk today, most of it. Turns out there are 3 approaches, 3 ways of doing it. Okay, first is the a priori approach, which means first you make a decision of among the objectives, which one is more important, which one is less important. So one of the things we've already, 2 of the methods or few methods we have already looked at. One is the weighted sum, okay, which means you have already decided on a weight vector. And the weight vector can be directly related to how important your objective is. So if I say that I'm going to use 0.75 F1 plus 0.25 F2, usually their weight, the sum of the weights is equal to 1 because you distribute 100% importance among the objectives. So if this is my objective function and I have already decided before I do any optimization, what you have said that F1 is 3 times more important to you than F2. Okay, by putting these weights, you've already given that kind of information. That's the a priori part. But believe me, this is difficult to do. In any practical problem, you ask even the practitioners, they might say, yeah, I want to give more importance to F1 than F2 because this is cost and cost is most important, fine. But now you go and say, can you give a number? That's where they are not very comfortable. And that's where people differ from one decision maker to the next. So these numbers are difficult to come up with. But if you change this to even 0.74 and 0.26, you might get a completely different design, completely different solution. So it's very, very important to, if you are doing a priori, you make sure the numbers you are giving is what you mean, okay? But in many cases, I was sitting in a presentation from someone from University of Michigan. They have applied weighted sum approach for nurse scheduling problem. So it's a hospital, and the University of Michigan hospital is really great, and lots of departments, big, huge. Even from East Lansing, we go there for anything. So so that has lots of nurses, of course, and then you need to schedule them, right? Who is going to come when? This need not be nurse scheduling, it could be janitor scheduling, it could be classroom scheduling, any of these things. So in that case, every person, the nurse is not available every time. Some prefers to work in night, some prefers to work during the day, some doesn't prefer to work on the weekends. And then every nurse has some specialty, and a particular ward needs to have a combination of specialty nurses, right? Not just of the same type. So there are a lot of constraints, as you see, and if you have to schedule it for a week, and then maybe you will be repeating it every week, and you have like 50 nurses in your roster, and every hour for the entire 24 hours you have to do, and there are not one word but multiple words. You cannot do it by hand. You have to use the software. So these are done usually using a single criteria, okay, and usual criteria is that how well you have met the requirement, because you will not be able to meet some words, some hours during the day. Probably there is no diversity of nurses because it's not possible. But then you put some of the nurses on call, saying that in case we need, we're going to call you. Okay, so all these you do, but then you come and you can put like a couple of criteria. One is from the hospital's point of view, how well you have matched or you have met the requirements, and the other one can be from the nurse's point of view in a cumulative way. That are the nurses happy, which means nurse have told you I'm available here between this to these days and all that, but you still had to schedule some nurse out of that time schedule because you want to also satisfy the hospital's needs. And sometimes they are flexible, you may have to pay overtime or some extra money. So how are you satisfying the nurses and how you're satisfying the hospital's needs? So if you just take these two criteria, there can be a conflict. Something that is excellent for the hospital may not be good for the nurses, and vice versa, right? So in that case, you have F1, F2, and this person is presenting, and he actually said that hospitals need was 75, I think this is 67%, and this one was 33%. So twice, hospitals need are twice as important. So I raise my hand and I say, how do you get this number twice? And that's where he kind of smiled and he says, it's very, very difficult. But they sat with the hospital board and the management board and everything, and they've come up with this decision, that's what they're going to use. But the result that they would get is totally dependent on that. Of course, these things are not announced. If they're announced, the nurses will go on strike, right? So because you are giving them like half the importance as the hospitals needs. So you don't announce these things, but you just keep it secret and you come up with some schedule. But you see, that's what happens when you do a priori. So you have to kind of approximate a lot of things. When you are doing a priori, you are fixing everything. So you have a single criteria. All you do, you don't need to even use EMO. You can use single point point-based optimization, or even a single objective evolutionary method, right? So that is one most common way people do multi-objective optimization, end up with one solution. So at this end you're getting one solution, right? And I kind of hinted yesterday, that's not what our principle is, and that's not what in my experience, the industries want. Industries would like to have few solutions if you can provide, and let them decide which is the one they're going to implement. So a posteriori comes for that purpose, that you don't do any decision making before you do any optimization. First you optimize and get a Pareto set, and then go to the decision maker and make decisions. So in the case of that nurse scheduling problem would have been that the optimization people who are presenting that paper would have found 5 to 10 different alternate schedules. So these are 1 week long, but you have 1 week schedule long, different, maybe 5 to 10 different ways you have these schedules. Every one of them has an F1, how much it satisfies hospitals need, how much it satisfies the nurses needs, and maybe some other auxiliary things that you may compute. With all that, you then go to the management and then discuss and say these are some alternate ways of solving the problem for this month maybe, and let them decide. Maybe this month is little lean month, and they may say, okay, we're going to give a lot of importance to nurses, and we're going to go maybe 50-50 or 60-40-60 or something like that. Next month is usually busy month because it's the season change and a lot of people get admitted. So we are going to be looking at more hospitals needs or something like that. Who can decide that? The person who is optimizing usually don't have that power, right? Usually it's a higher level decision makers can decide that, and unfortunately they are not the optimization people. Okay, they want solutions, they cannot get the solutions themselves. So there is a mismatch here, right? So what this lower level people can do is come up with number of alternate solutions, provide it to the decision makers, and decision makers give you a good nice pat if you're doing that for them, right? Because you're giving them with number of options. So that's the approach to me should be used, okay? And slowly but surely this is getting into the mainstream, okay? I am part of a software, Siemens, there are one person at least from Siemens here, from Siemens software called HEADS. So I am in their consulting board. So I attend their users group meeting every year. That take place in US. I guess there is one users group meeting here too in India. That meeting, all the users who are using come, and it's a good opportunity for them to ask questions or tell them what they need more from the software and all that. So they invite me to come always there, and I usually give the first talk on about 30 minutes about what's going on in the field. And then I'm there the whole day. So a lot of people crowd around me and ask a lot of questions about where this is going. They have a peculiar situation and how I would solve it and things like that. So I'm seeing that many of the industries have graduated now to 2 and 3 objectives, not beyond that. There are very few who comes with a 5 or 8 objectives, but that's about it. I will show you one with 14 today. But we've done some work with auto industries with 11 objectives, for example, 9 objectives and things like that. Sometimes they come, but very, very rarely. But that's a big step. In last 5 to 10 years, they were only doing single objective. All the softwares could only do single objective. And now the softwares are available, the same software, an extension with multi-objective. And so they are exposed to that, and the industries are trying that. So 2 to 3 most industries are using these days. So they want to at least see the trade-off and find some solution. So these software industries are helping us propagate these ideas as well. So here, when you apply the EMO, you get number of solutions, then you also have to make that MCDM part, the multi-criteria decision making. This is something I'm going to talk about today. Then I think the future is in this interactive approach, not doing the decision making first and then a single objective minimization, or multi-objective minimization and then decision making and optimization together. So I'm going to show you at least one idea there of what you could do. So back in 2008, so 2004, I started this Dachstuhl seminar series that always is in Germany. There is a Dachstuhl. There is a castle near Saarbrücken, the southern part of Germany. It's a nice remote place with a nice castle kind of nestled around lots of trees and little hilly area. It's a beautiful place. This is a castle now belong to the government. So every week there is a program on computer science area. So you have to propose these days 3 years ago to get a slot. Okay, it's very, very popular. It's very, very subsidized. Okay, it's like about $50 a night with food and accommodation, and the whole castle is with you. So for 50 euros, it's really, really great. And we've been doing it. I started it in 2004. And then every other year, but now as I said, it takes 3 years. So now it's every 3 years we do it. Second time we did, that was 2006. We thought we will have a purpose of doing it. First time, I brought 30 people from EMO and 30 people from the MCDM, because we thought we need to merge, we need to understand each other before we do this whole thing together, right? So I got together with some couple of people from MCDM who are well known, written books on that topic, and I've got one other colleague of mine, Branke, Jürgen Branke, and two of us from EMO, two of them from MCDM. We invited about 60 people. That's what this castle can accommodate. 5 days, you cannot come a day later, you cannot leave a day early. All these are requirements. If only you can, you come, okay? And then everything is taken care of. You can't do much because there's nothing around there. Okay, so but this castle is really wonderful. Lots of games you can play and evenings and all that. So what we did was the second time is that we are going to have a book at the book proposal at the end of that 5-day, and we're going to figure out the name, the title, the chapter heading, and all that, and who is going to write these chapters. And the criteria was there should be at least one person from EMO and at least one person from MCDM for every chapter. Besides some of the introductory chapter where, for example, I wrote one on evolutionary methods. There are Kaisa Mitanen wrote one on the classical MCDM methods and all that. So besides 2 or 3 initial introductory chapters, rest all are that. So we mixed very well. Now I know most of the key players in MCDM. And I ended up spending a couple of years with some of these MCDM people to know more what they do these things. So this book is very nice that way. It's a collaborative ideas of EMO and MCDM. Okay, so I'm going to start with a priori, although we've a little bit talked about like weighted sum and others. These are the 2 approaches I'm going to talk about, but spend a bit of time with reference point approach. Then there are other, I may show some results with that, not everything. These are some old method. Okay, I'll probably going to show you some plots or something with that. Otherwise, I'm going to just tell you what these are a little bit. This one I will go a little detail, and this is the one I said it's not in your booklet, but Dipanshu may have forwarded you the AHP slides or not. Okay, so I'm going to send you during the break the AHP slides, and then Dipanshu will send you. These are some commercial or semi-commercial software, because these are public domain as well, and there is a commercial version as well. And Dipanshu have really worked a lot on the Nimbus, and there is another one called Pareto-RES. These are the 2 things he worked on, because when he presents tomorrow about his ISOM methods and how visualization can be done with them, we thought we could take those ideas and redo the way they do Membus, and any of these things can be redone with ISOM concepts. So he's going to show you at least one of these methods. Prometheus is another popularly used one. So we're going to talk few of these out of here. So that's all a priori. So let's talk about the reference point method. I've already showed you this, I think, that when you have an aspiration point, right, So you're saying this is my objective F1 I want to minimize, my objective F2 I want to minimize, and I have an aspiration that with so little money, if this is cost and if this is environmental effect, I want so much environment, because I know that if I spend less money I cannot get too much environmental benefits, right? So I am not bad in aspiring, I'm not totally impractical, but I may also want to give this one along with this, saying okay, I want to spend like 4 times more money or 5 times more money, but then my expectation is very, very low emission. So I probably can come up with one other or maybe 2 or 3 such aspiration point, and I say give me a Pareto solution with respect to this. So this one, you see, these two do not have, I cannot give you a solution like this because all the solutions are in the gray region. This is my Z bar, right? There is nothing on the white region. So you are optimistic to achieve this. But what I can do is I can give you these points which is close to that and on the Pareto set. For this one, I can give you these ones. And if I have this one, I can say, yeah, what you gave me as your aspiration point, I can give you a solution, but I can even give you better solution because any of these thing here is better than that with respect to both objectives. And you are going to make the person happy because that is his aspiration. So he's been a little pessimistic actually for that, but you are going to provide some nice solutions. Okay, so the goal is then, given these 3 points, to come here, here and here. Your goal is not to find anything here because this is also Pareto optimal, or here or here. Your goal is not that. Goal is to only find this. So how would you change, for example, NSGA2 or any of the EMO algorithms so that you don't find the entire Pareto set, but you focus at Pareto part close to each of these aspiration points. So that's the R NSGA2, reference point based NSGA2, which we have developed. I'm going to give you an idea of how we did. So this is a priori because you are providing these decision making aids right at the beginning. And the goal is now go and find that part of it. You could do this for 3 or more objectives. Now if this is one of your reference point, this is another reference point, you get this patch and that patch rather than the entire Pareto surface. Okay. For reference direction method, it's slightly different. What it is that you provide a direction. So you have a starting point, and that can be one of your aspiration point in 3 objectives. For example, this is my aspiration point, and this is where is my worst aspiration. So usually this is your trade-off direction. There is a 3-dimensional slope you have. That's your in case of 3 objectives. That's usually this is your nadir point or ideal point, and this becomes the opposite. But you can give any other 2 points. So you say I want to go from here to there on this 3-dimensional objective space here. So then the idea is you take few uniformly distributed points along that line, and for each of them being an aspiration point like in reference point, you project them onto the Pareto surface. Maybe this one goes here when you like this one is going there, this one goes there, that one goes here, this one goes here. So like that, as you are moving along this line, straight line on the objective space, you are falling on the Pareto surface with this point. So you will be moving in this direction. If you give another line, maybe you move in another way. Okay. So this is called reference direction method because you are providing a direction. So the a priori information here is the direction, your starting point, your end point, and the gap in between that you want. So what's the big deal here? So this could be a part of this. You can actually take all of these points and say these are all my reference points, and your EMO algorithm like here is giving you 3 places. Here it will give you also, if there are 10 points, there will be 10 places, but it will get very crowded if you do lots of points around each. So you can pick one that is the closest from each, and then you can provide them here. Okay. Idea is as the decision maker is moving this way, so this could be the worst one like nadir point, call this nadir, and this could be your ideal. So you want to come from ideal to nadir. I'm going to give you an example why. So you are moving in the direction of all objectives being improving. You want to see what are the respective Pareto optimal solutions. So you will be keeping a close track of these solutions, how they are changing. Maybe at some point you say, wow, that's great. Let's not go any further. I got what I wanted. Or you may end up all of these and you're still not happy. And then you change the direction to another direction and keep doing it, right? So all these kinds of it's a little interactive, as you see, interactive methods, but a priori. Most decisions have been made early on. Okay. Now the story for nadir point to ideal point is very well known in the MCDM literature, and I have personally applied this in my life, and I found benefits of it. So that's why I want to tell this story to you. So we were going to Finland for a couple of years of stay with family. Okay. So my host Kaisa Mitanen, who is one of the big shots in the MCDM area. So I knew her from before, and then my wife and I went there first for a couple of days just to see where we are going to stay and where the schools are, talk to schools about our kids and everything. So we went there, and then she said, we're going to show you 3 houses. Okay, so she already figured out 3 places within the Helsinki city. And she took us to the first one. She was using a strategy. She didn't tell us. Okay, she took us to the first one. It's in a very crowded place. Okay, and also a little away from the schools. We went there and immediately kind of came out, and we said, can we go and look at the second one? She said, yes. So then we went to the second one. It was a little closer to the city, but a little away from the school. It was a little expensive. Then I said, let's go to the first one. And that was perfect. Okay, close to school, reasonable and everything. Then she revealed to me, then she applied this trick on me, that she starts with the worst one and then goes to the better ones. And that's how I was happy at the end, because if you show the best one first, you already have high expectation. And then if you go to the worst ones, you think that she's not showing you the right ones, because she already showed you the first one, which you liked, and you are looking for better ones and you're not getting it. So I don't know whether these shopkeepers here, like the shariwalas and all that, the ladies go and buy, whether they use this kind of trick, but all the people I know in that area, like we always buy dresses or sharis from one place, I told them, use this strategy because it helped in my life. Imagine the person showing sharis that are little expensive, not so looking good. If not, they should get some such saris, just not to sell them, but to put the buyers in the right direction. So you always should show not your best one. Okay, you should keep it for the end. It seems in MCDM literature, it's a well-known fact, but it's not out there yet. I don't know how many of you knew this, but this is a good trick if you have to buy something, or if you have to convince someone with something, try to use this with multiple solutions. So this is what they do actually. They go from nadir point, which is the worst of the Pareto solutions, towards the ideal point. Okay. So that you could do that on higher objectives as well. So let me spend a bit of time on the reference point. So I showed you this plot. The reference point for one aspiration point, you actually formulate maybe I should show you, okay, maybe I should go back to that first because I have left out few things there. Okay, so it's the same figure as I have also on this lecture 5, right? The aspiration point, and then you provide a weight. That means so what weight you are going to give to F1, that's called W1, and what weight you are going to put to F2, that you give W2. Notice that W1 I put it vertical along the direction of F2, because that's how this formula, if you use this formula to find this point. So if you solve this, if you minimize this, means minimize max of this, so it's a min max problem. When you do that, you are going to get a Pareto optimal solution. This is guaranteed. There is a proof that if you solve this problem, no matter what positive W's you use and what Z bar use, doesn't matter. Z bar can be here, 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 anywhere you feel like. The result of these is always one of the Pareto optimal. So in fact, it is one of the weak Pareto optimal solutions. If you have a weak part here and a weak part here, you can get any one of these, or anything here. Okay, it's guaranteed, never going to be anywhere else. So that's a good thing to have, okay, as a proof. Couple of things I'm going to suggest. You see, this can only be visualized in two objective space, because the W1, if you follow this, W1 actually is the slope of this line where you will hit the Pareto set. W1 is unfortunately along the direction of F2, and W2 is along the direction of F1. So what do you do when you have three objectives? Which direction W1 goes? Is it F1, or F2 or F3? It's a little bit of a problem. So what you could do, you can simply say, this one I'm going to do 1 over W1, and this one I'm going to do 1 over W2. You still have the same slope. Now W1 is associated with F1 and W2 is associated with F2 direction. And then if you have 3, you just do 1 over W3 there. The problem with that is you cannot use W1 or any W equal to 0. You can, but then you say this is very large weight for that if you are making W1 equal to 0. Okay, so that's that. So if you are using that, all you have to do is this one have to be changed with divide by Wi and max I going from 1 to m, and this is the one you minimize. So this becomes your ASF function. So you just put W as 1 over W, inverse of that, and then you have this figure that I have got. So that's the first improvement we did, so that we can practically see which direction things are going. Now max function is in the objective function. So ASF function is this function, which is my objective function, which has the max function. It's like max of 2 things, right, or more than 2 things if you have. So if you have 5 objectives, there are 5 functions like this, each one with 1 f, and you have to kind of take the max of that. Is that a differentiable function? So in some sense, if this is my x, this is my one of the function, this is my another function. What is the max function as a function of x? Will going to be max of these two is this until here, and then it is this, and then it is this. So this is my max function. Is this differentiable? Look at this. This places it's not. This places yes, if the original function is differentiable, but there are kinks. So overall this function is not differentiable. So some of the classical point-based methods like fmin-con and others, you will have difficulty solving them. So what they do, they make a smoother version of this problem. What they do is they introduce a new variable called alpha, and you say I'm going to minimize that new variable alpha subject to each of these terms. So I'm going to be using by Wi. This term, each term here is less than equal to alpha. So since each one of them you are satisfying to be smaller than alpha, you are basically alpha and you are minimizing alpha, your alpha will set as the maximum of all of these, because if alpha is equal to the max of all of these, that's going to satisfy for all your constraints. So it's an indirect way, by introducing a new variable, you are making your problem smooth. Now alpha is differentiable, it's just the last variable. It's actually linear. If fi is differentiable, this function is differentiable, and there are many constraint functions are all differentiable. So this is a differentiable problem. This is not. So people prefer to solve this, add a variable, but solve a smooth function. So that's another second modifications that you could do. But the thing is, once you solve either this problem or that problem, you are going to get a Pareto set. What happens when, let's say, your z is here, z bar is here, and this is your direction where your line doesn't intersect with the Pareto set? Then when you put that z over here, z bar, and this w, what will be your result? Because it's not hitting with the Pareto set. Here it did, right? And that's why I said that's going to be the result. What will be the result here? Is it going to say no, there is no solution? No, actually what happens, you get this point, and that's what I'm going to talk about next. So what happens when in this case? Oh, let me see if I have that plot. Unfortunately not. Okay, I need to make that plot. So let me find some white space to do it. Yeah, maybe here. So yeah, question, go ahead. No, originally this were, if you follow this principle and write the contour plot, okay, you will see that this line will have a slope of W1 over W2. Okay, it's simply because even if you say z is 0, you have weighted sum, right? W1 F1 plus W2 F2, that's your composite function. And for contour plot, let's say this is some value, let's say alpha. So what is your F2 as a function of F1? Will be alpha minus W1 by W2, alpha by W2, W1 minus W2 times F1. So your slope is minus W1 over W2. And so that's that slope, minus W1 over W2. It's going to be in the negative direction. So yeah, these will be your lines of or iso thing lines. So this is going to be your minus W1 or W1 by W2, and it is always going to be in the negative. So you see, any business like this, you have W1 gets associated with F2 and W2 gets associated with F1. So this one is very difficult to extend for more than two objectives, right? Because what do you, if you have three objectives, what do you put here on the vertical? Is it W1 or W2? But if you say no, I'm going to change my function so that I'm going to make now F1 over W1 and F2 over W2, and now if you redo this, it's going to be F2, which is W2 over W1 minus F1 plus W2 times alpha. So now my slope is W2 over W1, okay, which means W2 will now be on the y axis, on the F2 axis, and W1 is going to be on the F1 axis. So just redefining your weights as not just the weight but the inverse of the weights, you graphically you achieve a meaning of these W's. Does that make sense? Okay. Any further question? Anyone has? No. Okay. So it's a bit of geometry actually. So what I'm going to show, so let's say I've got a z bar and I've got a line. Okay. So if you look at that contour plot, if I have a point here, okay, and I'm saying what is the ASF value of that point, let's say this is from my x1, x2, x3, I get to that point, so this is my x vector, so my ASF at x, ASF value at this point, if I do it 1 over w, so it's basically F1, max of F1 minus Z1 bar over W1 comma F2 minus Z2 bar over W2. So that's my ASF function. So let's try to do this. So this is my F1 comma F2 point. Okay. So F1 minus Z1 is this distance. Okay. Divided by W1. So let's, for the time being, let's say W1 is equal to W2. So I can see this. 1 over W1 is 1, 1 over W2 is 1. So let's say I put them as 1, 1. So this is basically F1 minus Z1 bar, and the other one is F2 minus Z2 bar. Now, which one is bigger here? So I have to take the maximum. In this case, looks like this is bigger, right? But let's say I have a point here on this line. Then this is still my F1 minus Z bar, and this is my F2 minus Z by W1, right? So this I am kind of dividing by 1 over W2, and this is 1 over W1. Okay. So in that case, which is maximum? It looks like if this one was bigger than this, but now I made this shorter, so most likely this is the maximum. In fact, any point that falls here on the line, both are equal. Okay, that's how these W's are set up. So if you have any point on top of this line, then this becomes bigger. If you have any point over here, anywhere here below the line, first one is bigger. Okay, so now if I say, okay, here there is some value that's coming corresponding to this value here, the bigger one, because this is above the line. Let's take another one maybe here along this horizontal line. I have a new F1, F2. What is the first one? First one is this little thing now. Okay, F1 minus Z1 bar. What's the second one? It's still same as that one. And you have already seen when the first one was this much and the second one was that much, second one was bigger. Now I made the first one even smaller by coming here, still the second one is going to be bigger. So any point you take here, second one is bigger. and in fact they are all equal because I put a horizontal line. All of them are decided by the second one and all have the same value because they are on the horizontal line. So ISO ASF line, the same ASF value comes for all of these lines, all of these points. It's the same ASF value, and you can also argue that and go over this side all the way till you come and hit here. When you hit here, now you have this value which is same as the other one, and you also have a little bigger this, and they are going to be equal. So this is equal to that. Okay. Now what happens when you come here? Take a point here. Now your this value, which is the second one, is little smaller than that, and this one is still same as that. So which is bigger? The first one. So, and the first one is equal to the second one of that. So this point A and this point B has the same ASF value, and that happens as you go this doesn't matter where you are. So if there is a line which is determined by your W1 and W2, if you give me a point here, I can draw a ISO ASF line this way. I join the line with a horizontal line, hit this line and come down vertically. All points on these two lines have identical ASF value, and that's equivalent to whatever is the ASF over here. Now so let's say this ASF value is 10.5, and I have another point here, its ASF value has to be smaller, it will be like 5. So as you come down like this, your ASF reduces, okay, and if you can go even below until here, what is the ASF? The distance is 0, all of them are 0, so this one will have a 0 value. This contour line, when it hits your Z bar, you have a 0 value. When you go below, you have negative value. So here you have negative ASF, here it is 0, here you have positive ASF, and as you go that way, your ASF increases. And remember what we do, we always minimize the ASF. That means our goal is to come this way as much possible as this way. So if I give you a problem where, let's say, it's a multi-objective problem, F1, F2, and I have several points like this. Let's say I have a Z bar and a corresponding W and a Z bar, and I ask you, can you rank these 5 points in worsening value of ASF? You know, largest one is further away from Z bar, right? As you come to Z bar, your ASF is reducing. If you cross Z bar, then it's even better, right? So going in this direction is always better. So how do I rank? So to do the rank, you need to plot these contours. So for every point if it's above the line, you have to go horizontally, hit the line and go down. So that's your contour line. You basically need to know where it hits this. This one maybe slightly above, and this is your hitting. This one you have to go up, because you see all the ones below you have vertical line, and go that way. This hits over here. Call this 1, 2, 3, 4, 5. So this one I did 1, now this one 2, this one 4, this one 5. And where is 1? 1 is going to be here, 1, and 3 is going to be here. You see how I have moved from 3 up first, hit the line and then go. So now you look at where they are hitting, you see, and this way is better, right? So the ranking is 1, then 3, then 4, then 2, then 5. So now this is how we scalarize multiple objective into a single scale, single objective with this ordering. For 1 is better than 3. So if you look at the original points, here is 1, here is another, here is another, here is another, and then the last one is here. You have no way of saying their order, because they are in this two objective space, they are all scattered, very difficult to say. But as soon as you give me a Z bar and a W, I can simulate this process and order them. You see, 1 is better than 3, 3 is better than 4, 4 is better than 2, 2 is better than 5. Right? If I change my Z bar, keep the direction, I may have a different thing. If I change the W and keep the same Z bar, I may have a different thing. So given Z bar and W, I can order any number of points. Okay, so that's clear, right? So that's why the ASF is so important. I'm not going to go into the ASF, but just to say that with ASF you can find any point on the week as well. If you do the augmented ASF, then you only find the Pareto, not the week. But that's all I'm going to say here. Let me now go back to, so that's the origin of this figure, and then what you're going to do is we're going to modify now NSGA2 to find them. So how? Remember we had crowding distance in NSGA2. We do tournament selection. If you are from the same rank, we're going to look at crowding distance, and if you have a higher crowding distance, we select you. Here we forget that, because that's going to find the entire Pareto set. Here our goal is to find only near each of these points, and multiple reference points are given. Okay, so what we do is, I may have a figure here. I've actually deleted those figures for some reason. So we systematically do this. Like if you have lots of points in my population, let's say there are other points in my population, and I have one reference point here, another reference point there. First thing we do is go and find the closest point to each reference point, closest one. So we are forgetting crowding distance. Okay, rest of the algorithm is still the same. So for reference point RP1 and RP2, we pick the closest one first. So those are selected already, and we do this front by front. So we first identify the first front with respect to RP1 and go and choose the best one. And then there is a concept of clearing, that actually one of the niching ideas which we haven't talked about, but there are many niching ideas. So there is a epsilon concept, that once we found this, within an epsilon ball around it, we are not going to select any other solution. So even if you have a solution here, we are not going to do this, because we want to have some difference between the two. So next one is, let's say next closest is that. So I'm going to pick, so this is the first one I picked for both, then I'm going to pick the second one, and I'm also clear with this, and maybe this is the closest, I'm going to pick that one. And then I'm going to clear again with that, clear with that, and pick the next one, which is maybe this one, and then this one, again clear. Like this we keep filling my population. So once I'm done with all of these points, then I move to the second front and apply the same process, which is the closest to the second front, clear, move to the second reference point, clear, and all that. Okay, so the crowding distance is gone. We just concentrate on these reference points given and go to the closest ones, clear, closest one, clear, like that we fill. Now of course, since we are calculating distance in this space, F1, F2 space, we need to normalize. With the given population diversity, min max, we again normalize and then compute the distance. So it's a simple change to NSGA2, we call this R NSGA2. We could define the distance with weight. So if you prefer more for F1, we can actually put a W1 which is higher than 0.5, and then we'll be preferring solutions. So what happened is, okay, maybe there is a plot here, yeah. So let's do the weighted one later. So in this problem I have two reference points, and you see this is my entire Pareto set, the line, and this is what I get. These two I get simultaneously at the end of our run. This generates that, this one, and this generates that, and that's the end of the run. Second plot I show is when I've increased my epsilon. So I said now I want a bit more distance between each of these points. You see the spread has increased, but it's in the same area. Now to show the difference, I have shifted them up a little bit, but they are actually all on the Pareto set. As you increase your epsilon, you get more and more spread. So if you want more solutions with spread, then you have to use a larger epsilon, and that's at some point epsilon is so large that they kind of mix with each other. Here's the effect of distance. For single reference point, this would be, if I do equal weight in my weight description, then I get it in the middle. But if I do more weight for W1 and less weight for F1 and less weight for F2, then you see I am preferring smaller value of F1, right? So you see these points have now moved here. So it has little bias. If you want more solutions with smaller f, then you give more weightage for F1, and then your points move a little bit, because my distance is not now this distance, my smallest distance are going to be like this now, because I'm over here it's more important than over there. Same thing is the opposite here. If you do more importance to F2, you get here. Same algorithm, just changing these weight over here, you can achieve not at the center but somewhere on the side if you want. Okay. You could do this with multiple reference points simultaneously, as you see that we always achieve, whether it's concave, convex, doesn't matter. This was little interesting. I decided to put one reference point in the middle of two parts of the Pareto set, because remember this problem I showed you, here is the Pareto set, it's disjointed. Okay, these red lines are my Pareto set. So when I give a reference point here, come on, this is a bit far away than this, so it finds the shortest one there. This one almost equidistant, so it finds something here and something there. When I give here, now this one is closest, but this is not Pareto set, right? So it finds over there. But you see, this point, which is not a Pareto point, because if you had a B point, it could have dominated A. But why I find this? Because I don't have any pressure for finding a point in B. If I given one of the reference point here, yeah, then I could have found some point here, and because I am finding all of them in one run, A should not have been there. But because I don't have a need to find B there, nobody is dominating A. So this method is non-Pareto. You may end up finding some points that are not Pareto solution. Okay, because you are not finding the entire Pareto set. So unless you have the entire Pareto set demand, you will not get the true Pareto front. So this you have to be aware that this can happen. Okay. 3 objectives, I showed you results. These are 5 and 10 objectives, you could do that too. Okay, there is a concept of cone domination which I already introduced you, the cone, right, the obtuse cone or acute cone. Here is a way to achieve it. How do you use this cone? So you can simply go to your NSGA2 code and redefine domination. That will be the best. The other thing you could do is, I don't have the source code for NSGA2, or I don't have time to understand the NSGA2 code. All you can do is redefine your objective function. You have your original objective function as F1 and F2. Based on the slopes, you redefine your F1 as omega 1 and F2 as omega 2, but these are combinations, linear combinations of these functions. So now you send these two to NSGA2 rather than original F1, F2. If you do, you are only going to find this proper part of the Pareto set, and which is dictated by these slopes. So by changing the slopes, you can find different parts of the Pareto set. So see, here is the result. You see, when you do NSGA2 with that change, we only find from here to there in this case, and we don't rediscover this part, because this is only going to find a part of it. If you change the cone to something like this cone, this is vertical, then you are going to get this part. Okay. So with this idea, later on we came up with a distributed computing approach where there are multiple processors. There are 3 processors, P2 and P3. To each processor we give a different cone. For example, the P1 we give this cone, P2 we give this cone, and P3 we give this cone, where these are parallel and these are parallel. Okay. So this is supposed to find this part, like you see here. This one is supposed to find the middle part, like you see here, and the other one I don't have. This one P3 is going to find from here to there. So this is P1's job, this is P2's job, this is P3's job. Now you have 3 different processors. You have defined a different cone with some common properties so that nothing is left out, and then let them individually optimize, and once in a while you migrate the good solutions to see that which one has converged better or things like that. So there is some details there, but at the end you are going to get these solutions in different processors, put them into a central computer and say this is my entire Pareto set. So you have distributed the task of finding the entire Pareto set among 3 processors. It will be faster to find each of them, and so with the help of multiple processors or parallel computers, you have actually reduced the time of finding the entire Pareto set. For 2 objectives you don't see much difference, but when you go to higher objectives you can actually do this very nicely. Okay. So this cone domination is, or proper domination as we talked about, this is very, very helpful to do that kind of stuff. Okay, so those are a priori approaches where you are making a decision either for the reference point, reference direction, or cone, defining a cone beforehand. So when you define the cone, your entire Pareto set is not your target. So already you made a decision of where you want to focus, right? Those methods can also be used as an a posteriori approach. So the whole concept here is you go and find a Pareto set, like for example in this case, let's say this is my Z bar or Z, and I go and find a set of Pareto solutions by NSGA2 or some other method, okay. So optimization is done. Now I have to pick one. Just the other day, 2 days ago, I was meeting with the professor here and he's already working in multi-objective. This is the only decision making he uses. And I have seen that many people in chemical industries, distillation towers or any other process optimization, they do this. What is this method? Once you find these points, and this professor is fortunately told me he uses NSGA2, so he came to see me actually. So then what you do is you get this point, which is the ideal point, derived from your Pareto set, right? The point that is best for F1 and best for F2, and then you normalize. So that means this is 1, this is 0. I am telling you all the time this normalize because it's so important when you do anything with F1, F2 combination. So all the points are within this box of 0, 1, 0, 1, right? Now what you do, from your ideal point, you see which one is closest in the Euclidean distance sense, and that's your pick. You are not going to any decision maker and saying, is F1 more important than F2 or what? You are just geometrically saying, I have these location of the Pareto points, I'm going to pick the one that is closest from the ideal point. What's the logic of doing that? Because so many people are using it, there must be a logic. Logic is everybody wants to get the ideal point because that's the best combination of F1, F2. So you're saying, okay, you got bunch of solutions. Which is the one that's close to my ideal point, my ideal solution, and that's the one I'm going to pick. It doesn't matter whether it's towards minimum F2, towards minimum F1 or what, I don't care. This has least difference in the objective values from my ideal point. It's a little lazy way of doing it, but that's usually you see a lot of papers where they put this kind of circle showing that you come the closest from here. So this is also known as compromise programming. Instead of circle, you can make it an ellipse. So you say, here is my ellipse, and I'm going to see which point makes my ellipse distance, elliptical distance that I have here minimum. So actually you can have any p. When p equal to 2, you have circle or ellipse. For ellipse you need a w also here. But you could do p equal to 3, p equal to 1, p equal to 5. You have a different distance measure. Basically some kind of weighted metric distance that you go from the ideal point. Is that clear? So that's one way you do a posteriori. You are friending all these points, you are picking one based on some criteria. Next two are not that ad hoc. They actually utilizes some information about the Pareto solutions. This one I already mentioned, this is the trade-off method. So you need to define a trade-off metric. What is trade-off? So let's say I'm here and I'm looking at two of my neighbors, first one and second one. Now if I am choosing this one and not choosing its neighbor, I need to come up with what is my trade-off. So if I say that what is the trade-off from going from here to there, which means how much do I define my trade-off this way: loss to move to my neighbor, to gain in move to my neighbor. So when I go from, let's say, solution 1, 2, 3, I'm going from solution 2 to 1, how much I am sacrificing? How much is the loss? Can you point me? Is it the horizontal distance or is it the vertical distance? When I go from point 2 to point 1, which objective I am losing? F1 or F2? I'm by default minimizing. F2 I am losing because I am increasing my F2 from 2 to 1. So this is my loss, okay, and then this must be my gain, right? I am gaining on, so obviously if there are two objectives, one objective you gain, other objective you lose. So it's L by G, if this is your G. So that ratio is going to be your trade-off of moving to the left point. What is the trade-off moving to the right point? What is your L and what is your G? So which way I am losing going from 2 to 3? F1. So this is my loss. So let's call this moving to 1, L1 G1, and this is L3 to move to 3, my loss, and this must be my gain in objective 2. So the other one is going to be L2 L3 over G3. So these are two different numbers, right? One for moving to left neighbor, another one to moving to right number. So I can take an average. I can sum it and divide by 2, so I can take an average. So this is, on an average, I will be losing per unit gain, right? And this slope basically depends on where you are on the Pareto set. If you are taking some other point like this point, it will be a different average L by G ratio, right? Okay, so every point will have a different L by G. How about this end? How do I compute? Because there is no neighbor on one end. You just do one-sided. So basically you find L by G for this, moving to this, and that's it. There is no average. Same thing here you do. But I can define now an L by G for each of these points. Make sense? Now each one of them has this trade-off value. So I'm taking average here. Let's say this one is 2.5. This one is 1.2. This one is 1.9. I'm just giving some number, and so on and so forth. I can assign such a number because all these points are found first, so I can compute them. Which one shall I choose? Which one would be of my importance? Let's think about it. These numbers are per unit gain. What's the loss? Per unit gain in one of the objectives, how much I have to lose in making the move. So when I'm doing 2 to 1 or 2 to 3, I'm saying, what if I choose 2? How much I would have lost if I had moved out from there to my neighboring point per unit gain in one of the objectives? Will you be looking for the highest value of the trade-off or the lowest value of that trade-off? Is this intuitive? Okay, let me put it this way. It's true with everybody I talk to, okay? You are not the only one. It's not easy to just grasp it like that. So let's say I give you a solution and I tell you that if you want to move to its neighbor, either way, either side of the neighbor, per unit cost, let's say per unit dollar, you are sacrificing. So per unit dollar of gain, so per unit dollar of reduction of what you are now, you are going to save $1, but then you will have to increase the emission by, let's say, 5%. This is one solution in the Pareto set. Another solution in the Pareto set, I am saying, for $1 decrease from there, you will make only 2% drop, 2% increase in the environmental effects, in the pollution, right? So one, for the same $1 of reduction. So if you are dropping by $1 your cost, you expect that you are going to have what? So you are gaining in the cost. So you are going to have more pollution, right? Because you are saving $1 and you are going to have more pollution than from what you are. So I'm saying one solution gives you 5% pollution more for a reduction of $1 to make that move. The another one makes only 2% more emission. Which one is your preferable? 2% one? First, everyone says that, but it's always the opposite. Why? So that 2% or 5% is for you to make the move. So the smallest one, if you move, you are actually not sacrificing a lot, so you would rather move maybe there. So instead of 2%, if this was 0.5%, you say, yeah, I'm going to make that move because it's really not much of a sacrifice I'm making. But if another solution says no, it's 5%, so little bit of reduction, saving in the cost, you are actually have to sacrifice a whole lot. That doesn't motivate you to move to your neighboring point. So here's the one with 5% that says, I am not interested in moving to my neighbor because my neighbors are in worse situations than what I am. Now, can you answer my questions? Which one do you like? Because you don't have any motivation to move to any other points in the neighborhood. That means you like the solution where you are. So you always look for highest loss by gain, highest trade-off value as a measure of saying, I am not interested in moving out from here. I like this one because if I move, the trade-off is really bad. Okay, so you can then analyze like this all the points, find these trade-off value, which is loss per unit gain, and then you see which one is the highest, and that's the one you recommend. Okay, this is going to happen like if you have a problem with a knee, this kind of Pareto set, you are minimizing both. If you have a point here, this is called a knee point. It looks like a knee, right? It's more like an elbow, but opposite way of knee. So if you from here to take a neighboring point, how much you are sacrificing versus how much you are gaining. So again, this is your gain, this is your loss. If you come to another neighboring point, so this is your gain, this is your loss. You see, the loss is always bigger than gain, either way you go. So this point will have a very high trade-off value. The loss is much higher than the gain. Rather, if you have a point here and go to its neighbor, okay, here the loss per gain is not that high as over there, and the same thing is over there. Okay, so this kind of points will have very large trade-off, and people in industry like these knee points to choose them because they have very high trade-off. So if your Pareto front is this kind, very sharply coming down and very slowly going on the other direction, is this kink point is what they like because these have very high trade-off. So that's what we are trying to find here. Is there a kink kind of point? So in this case, I think I computed for these. This one comes out to be the best out of that. Okay, so it's not a distance from ideal point. It's basically analyzing pairwise how much you're sacrificing, how much you're gaining, because that's all people in decision makers do, right? How much I'm sacrificing on cost versus how much benefit I'm getting on the environment or some things like that. So this is highly practical. We often use this metric. Many problems we solve using this. Next one, third one I'm going to talk about is pseudo weight. Okay, what is pseudo weight? Every point that you found, you can calculate a weight. It's not the weight for the weighted sum. That's why I called it a pseudo weight. Here's the formula for deciding that. So what is that formula? For every point, you have the max and mean, this is the max for F2, this is the mean for F2, this is the max for F1, this is the mean for F1. So what you do is you calculate for every point the distance from the max. You see it's max minus Fi, and this one is max from Fi. So every point, go to their F1, F2 axis and then look at the distance from the max of the Pareto set because Pareto set is already known, right? And now basically it's the proportionate of this versus that. So in that proportion, you assign a weight. So you see this one is about 9 times more than that, so that's why I have 0.9, 0.1. In other words, saying if you are choosing this point, you are actually giving 90% importance to F1 and only 10% to F2 because you are very close to F2's worst and very close to F1's best because you are farthest away or far away from the F1's worst. So a point in the middle will have 50-50. But if you do a weighted sum with 0.5, 0.5, as we discussed, you will never get this point because this is in the convex part. That's why it's not the weight in that sense of weighted sum. And that's the reason I call it pseudo weight. Okay. But now the good thing is you can assign whether it's in the convex part, whether it's in the concave part, this weight, pseudo weight. You can compute using this formula once everything is there. Now that I have computed, I know sort of like equivalent weight that trading off these two objectives, giving the importance of the two objectives, I now have something in my mind that I'm looking for a solution with F1 giving 2 times importance to F2. I know it's difficult to do, but now that you have number of solutions, it's sort of like getting to buying a car, and you say, you know that the car goes from, let's say, 5 lakhs of rupees to 50 lakhs of rupees, and you can't go close to 50 lakhs. You say, my cost is as twice as important as the safety. That's the only thing you figured out that you want to choose a car from. So you look at all of these solutions, you compute the pseudo weight, you are looking for a solution with 0.666, 0.7, 0.333. So that's like, this one is twice of the other one in terms of weight. So now you go and see which one is closest to this. I would have liked to have a point here which is 0.666, 0.33, but I don't have, but this is the closest one I have. So my recommendation will be this. So this is the car I'm going to pick. You see? So first you compute pseudo weight for every one of them, and then you kind of match it with what you are looking for. That's not easy to do, I'm saying, but if there is a way, you have this number, then you can pick one which is closest to that. If you're not happy with that, you really want that, then you have to use RNSGA2. Give a Z bar or RP here, and then the points will come, lots of points will come over there, because now you are focusing there, right? And then you can find one exactly with what you are looking for. Okay, so again, this can be interactive.